this module, we are going to look at turbulent flows and how to do some calculations involving turbulent flows. Our primary interest would be to calculate drag on objects that are immersed in an external flow or pressure drop in pipe due to a turbulent flow and so on. So the problems that are of interest to us are primarily engineering applications. So we will not be taking a fundamental look into turbulent flows. We will only try to figure out how to do such engineering computations when the flow is turbulent, in contrast to what we have been doing so far, where we have assumed the flow to be laminar. It's well known that turbulent flows are inherently three-dimensional. Even if the velocity components are small, the fluctuations of the velocity components in all three directions are usually comparable in magnitude. And flows are also highly unsteady. So the fluctuations are also highly unsteady. So trying to obtain a complete description both in the time domain and space of a turbulent flow field is a daunting task and probably not possible at all. So one of the approximations or assumptions that was made very early in the study of turbulent flows is to give up this requirement that we need information both on the time variation of the flow as well as the velocity components at every point in space, and instead say that we are interested only in the turbulent mean flow and not in the fluctuations themselves. So this, it was hoped, would simplify the equations to an extent where the problem becomes tractable. So what we mean by this is illustrated here. The flow on the left shows the variation, or the figure on the left shows the variation of one component of velocity in a laminar flow. So it can be seen that flow is initially steady in time, and then there are fluctuations, and then there is a variation in time, not fluctuation. There is a variation with time on this velocity component, so the flow becomes unsteady. Now, if the flow were turbulent, the same flow field might look something like this. So here we see high frequency fluctuations superimposed on top of the mean flow field, which looks like this. So, so here we must make a distinction of two different types of unsteadiness. Notice that the mean component of the flow still shows variations with time at a much smaller frequency, meaning longer wavelengths, whereas the turbulent fluctuations are higher in frequency and they show rapid variations like this. So when we do a time averaging of this type of flow field, which is also known as Reynolds averaging, when a time averaging of this flow field is done, basically what we do is to take the flow over a certain time period, let's say capital T, and then compute the average that erases these high frequency fluctuations, and we are left only with the mean component. So basically what we are doing mathematically is this. So we take each velocity component which is fluctuating in time, and we write it as a sum of a mean component plus a fluctuation. So if you see here, we can see that the solid line here is the mean component, and there are fluctuations superimposed on top of the mean component. So that is what we are assuming when we write each one of the velocity component like this and the pressure also like this. So what is then done is when we do this kind of averaging, what we actually mean is the flow, which is the fluctuating component, any fluctuating component, when averaged over a time period capital T, gives the mean, which means all the fluctuations are erased and we get only the mean. So the important point is the averaging should be done over a sufficiently long period of time, T, so that the fluctuations are completely erased and we are left only with the mean. Now, of course, this also ensures that the mean of the fluctuations is zero because the fluctuations are completely removed. Now, if the mean flow itself is unsteady, as it is over here, this averaging is done in such a way that this T is long enough that the high frequency fluctuations are removed, but it still leaves these low frequency oscillations intact, so that if the mean flow is unsteady with time, that can still be captured. So the important point is that the fluctuations are assumed to be at a higher frequency, and the unsteadiness in the mean flow is at a lower frequency. So then this time averaging process erases the high frequency fluctuations, but not the low frequency variations of the mean flow field. Some additional mathematical properties of the time averaging process are given here, and these would be used when we derive the governing equations for the mean quantity. So basically, the strategy is to decompose the turbulent flow field into a mean part and a fluctuation. And now what we will try to do is try to come up with equations that govern this mean component, so that we have an idea about the turbulent mean field, even if we do not have the turbulent flow field itself. Okay, so what we do is we take the incompressible Navier-Stokes equations, and we substitute these decompositions into each one of those equations, and then we can actually arrive at these, after a little bit of algebra, we can actually arrive at these equations. So this is the continuity equation for the mean component of the flow field, continuity equation for the fluctuating component, I'm sorry, for the, this is the momentum equation for the mean component of the flow field. This is the momentum equation for the y component of the flow field, and so on. So we end up with 4 equations, which was what we had when we started out: the continuity equation and the 3 components of momentum equation. So in principle, we have 4 equations, each one of which can be said to govern the 3 components of velocity, and we can also come up with an equation for pressure from this equation. So we have 4 variables or 4 unknowns and 4 equations. But the difficulty now is that the term in braces shows additional unknowns that have been introduced into the governing equation. For instance, u prime square bar, u prime p prime bar. So there are actually 9 such quantities, but given the symmetry, for example, u prime v prime bar is the same as v prime u prime bar. So given the symmetry, we actually have added 6 more unknowns into this set of equations. So in addition to u bar, v bar, w bar, and p bar, we also have these types of unknowns which have been introduced: u prime square bar, v prime square bar, w prime square bar, and so on. So we do not have enough equations to close this system of equations. So this is usually referred to as a closure problem, wherein we have more unknowns than equations, and we are not in a position to generate additional equations to cover these unknowns. So what must be borne in mind is that the closure problem is a manifestation of the Reynolds averaging that we have done, and it is not the fundamental problem with the Navier-Stokes equations themselves. Okay, so this difficulty arises only because of the time averaging that we have done. But we normally can press ahead and do the following. We can actually take these terms which appear on the left-hand side. Notice that these terms arise because of the nonlinear terms that are there on the left-hand side, the convective terms. So these terms here under this or brace arise when we take time averaging of these nonlinear terms. And what we do is, although they arise as a result of averaging of the nonlinear terms, we take them to the right-hand side and combine them with the viscous terms. For instance, we can take them to the right-hand side and then rewrite the viscous terms like this. So we can see that each one of these terms is now combined with a particular viscous stress term. And this has a certain appeal, because it looks nice. The advantage of doing it like this is that there is no basis, but the advantage of doing it like this is that each one of these this average term, v prime w prime bar, u prime w prime bar, each one of these terms may now be interpreted as a stress term. So they were on the left-hand side, they would have been convective terms, but now by taking them to the right-hand side and combining them with the stress term, we are now able to interpret each one of these as a stress term that arises due to turbulence. So it's as if turbulence creates additional stresses in the flow field. So this kind of interpretation is possible by writing these terms like this. But it must be understood that there is no theoretical basis for this interpretation or for writing it like this. Okay, so what we do now is we gather these terms and then write them as a stress tensor due to turbulence. So you can see that the diagonal terms have terms like u prime square bar, v prime square bar, and w prime square bar, and all diagonal terms have products of the fluctuations. This tensor is called the Reynolds stress tensor, and it is symmetric, as we already mentioned. U prime v prime bar is the same as v prime u prime bar, so it is symmetric, just like our deviatoric stress tensor and the rate of strain tensor that we derived earlier. So now the stress strain relation, which connected the deviatoric stress tensor with the rate of strain tensor, now looks like this. There is an additional Reynolds stress tensor in this. The only the only change now is that the rate of strain tensor, which earlier used to involve only the velocity components, now involves the mean velocity components, the time averaged mean velocity components. That is the only difference from before. So, which means that we can write the deviatoric part of the stress tensor like this. Notice that this is the same as the deviatoric part that we wrote down earlier, with the u being replaced by u bar and so on. And this is the Reynolds stress tensor. Now, if we compare these two stress tensors, then it is actually quite tempting to write this term itself in the same form as each one of these terms, which would then allow us to combine this with each one of this. For instance, we may write minus rho u prime v prime bar as say some mu sub t times partial v bar partial x plus partial u bar partial y, and similarly for the other terms. If you do that, then we can actually combine this stress tensor with this, and the two together can then be written in a very compact form. And this is called the Business hypothesis, namely writing each one of this as mu t times its corresponding component from the deviatoric part of the stress tensor is the so-called Business hypothesis. So if you go ahead and do that, you can see that each one of this term now looks the same as its counterpart from the deviatoric part of the stress tensor, but now multiplied by mu t. And mu t is called a turbulent viscosity or eddy viscosity, and this is understood to arise from the turbulent fluctuations of the flow field. Notice that we are dealing with the mean flow, but the fluctuations still cause a turbulent stress, which is being accounted for through this single term here. Okay. Notice that the diagonal terms alone look slightly different from this. They are not exactly equal to 2 mu t times partial u bar partial x, for instance. This term is also required to make the equations consistent. So this is actually, so replacing each one of this term with a term like this is called the Business hypothesis. And the only problem is this replacement is ad hoc, and it was suggested by Business way back. Now, the advantage of the Business hypothesis is that it takes care of the closure problem. We no longer have these types of unknowns. All these have now been related. So the mean of the fluctuations, product of these fluctuations, are now related to the mean components themselves. So these are no longer separate unknowns. So it takes care of the closure problem, but it leaves us with one additional quantity, which is the turbulent viscosity mu t. Okay. Now, the difficulty here is that mu t arises is a viscosity effect that arises from turbulent fluctuations, and so it is a property of the flow, unlike the dynamic viscosity mu, which appears here, which is a property of the fluid itself. Okay, so the hypothesis, what it says is, it is as though the turbulent flow field effectively sees a viscosity which is a sum of the physical viscosity mu and the turbulent viscosity mu t, which is an effect of the turbulent fluctuations. So mu t is thus a property of the flow and not the fluid, whereas mu is a property of the fluid. Unfortunately, because mu t is a property of the flow, it will also vary from point to point, because the fluctuations, as we said earlier, are three-dimensional in nature and also unsteady. So it varies from point to point, and it also varies from one instant to another. So it is actually an extremely difficult quantity to evaluate. So capturing all this in one single term, all these effects, the fluctuations and the stresses due to that, in one single term is actually a very tall order, and that actually is the weakness of the Reynolds average Navier-Stokes equations. So the idea that all the stresses due to the turbulent fluctuations can be captured by one single quantity is actually a very difficult thing to do. So mu t cannot be determined exactly because we are not solving for the fluctuations. We are only solving for the flow field. So we have to develop models for mu t. So the basic idea in turbulence modeling is to develop appropriate models or expressions for this mu t, and the models have constants which can be adjusted to yield predictions which are consistent with canonical flows. These are flows, simple flows for which analytical solutions can be obtained, and the prediction should be consistent with these canonical flows, and they should also agree to the extent possible with experimental data. So the idea is to adjust these constants so that the value of mu t gives an overall consistent flow field that shows reasonable, if not good, agreement with experimental data for well-known simple canonical problems. So when we use these models for complex flows, we do so with the understanding that the models have not been developed for these complex flows, but the constants in the model have been developed only for the simple canonical flows. So consequently, any flow field prediction that we obtain for a gentle flow will be very sensitive to the values that are used for these constants. But over the years, these models have been tweaked and the constants have been fine-tuned to such an extent that the predictions have become very, very good, and agreement with experimental data has also improved considerably. But fundamentally, this is a shortcoming that remains, primarily because no single quantity can capture the turbulence stresses that are generated across an entire flow field. So that shortcoming still remains. Now, what is done is we mentioned at the beginning that it is very difficult, if not impossible, to actually obtain complete turbulent flow field for any given problem. Now, and we started down this road of averaging the equations and then relaxing our requirement that we will not demand the fluctuating components of the flow field, but we will settle for the mean component of flow field, was expected to make the problem more tractable. Now, it is tractable, but it is still quite challenging to obtain solution to the Rand's equations even with the powerful computers today. Although a lot of success has been made in solving many complex problems, there are still problems which cannot be solved even with the Rand's equations. But things have improved a lot. But the most important point from our perspective in this course is that this is not something that we will try to do. For instance, if we want, to calculate pressure drop for turbulent flow through a pipe, or drag due to a turbulent flow over a flat plate, we do not want to solve these Nancy equations to obtain the quantities like drag coefficient that we are interested in. So what we are actually looking for is to see whether, similar to what we did for the laminar flow, whether it is possible to develop simpler expressions that we can use to calculate pressure drop in pipe flow, or drag force on objects that are immersed in an external stream and so on, to an acceptable degree of accuracy for engineering applications. It turns out that it is possible primarily because the mean axial velocity profile. So if we have boundary layer flow or a flat plate or pipe flow, turbulent pipe flow, the axial component, which would be the component along the axis or in the x direction as we did earlier, the mean axial velocity component the boundary layer exhibits an universal structure that is independent of the Reynolds number. So whether the Reynolds number is 10,000, where the flow becomes turbulent, or whether it is 100,000 or 1 million or 10 million, the boundary layer for the mean turbulent axial velocity component remains the same. So this universal structure allows us to actually calculate quantities of engineering interest like pressure drop in turbulent flow in a pipe, or skin friction drag, or due to turbulent flow over a flat plate quite easily without resorting to solving the Navier-Stokes Reynolds average, Navier-Stokes equations, or even the full Navier-Stokes equations. So the universal turbulent boundary layer structure is what we will take up next.